Hello and welcome everyone to our talk about QEMU in the fast lane and how we accelerate KubeVirt networking with the help of eBPF. This talk and this project has been done in collaboration with my colleague Anton, Jussi, and myself. And yeah, to set the context a little bit, not too long ago, the virtualization landscape has been shaken up a bit. I found this quite an interesting quote from the MIT Technology Review in late 2023. A long-trusted virtualization staple became the biggest open question on the enterprise IT roadmap. So a lot of enterprises are now rethinking whether to stick to the current stack or whether to migrate and modernize the infrastructure, potentially going into the Kubernetes space because they have containers running anyway there. And the question is, are there any viable OSS solutions with help with that strategic reset to move the VM infrastructure into Kubernetes? And we think the answer is yes, that is KubeVirt, and together with Cilium to help with the networking. And then throughout this talk, I will detail you why that is. In general, so the combination of Kubernetes and KubeVirt basically enables users to converge their infrastructure. So you basically, previously you had two stacks. You had two logging solution metrics, monitoring solutions, one for your legacy VM platform, the other one for Kubernetes. And now you can migrate everything over into Kubernetes for both VM and container workloads. And that helps with the overall user experience, given that it's now unified. Just to give you an architecture picture in terms of how the KubeVirt networking side looks. So you basically have your Kubernetes node. KubeVirt is launching a Kubernetes pod, a launcher pod for the VM. So your regular CNI is setting up Weave devices, for example, with one Weave flag in the host namespace, one Weave flag in the pod namespace, and then KubeVirt is setting up a bridge device in a tab, and then it's launching QEMU, KVM as a VM, and it's basically connecting through that. And the IP address, it's getting through a DHCP, where you can then manage the IPAM. So we had, for this talk, we basically had so-called moonshot idea. Can we reimagine how we do the networking, like the VM networking in Kubernetes? And before I go into that, I want to go a little bit more to the fundamental side in terms of how we solved container networking with Cilium to remove the overhead there for Kubernetes pods. If you look at a standard Kubernetes pod data path, you have your pod itself as a network namespace, you have a Weave device pair, and traffic going in and out of the pod basically goes through the upper stack, to routing, to netfilter, and so on. And over the years, we changed that in Cilium with the goal to basically make those applications that are residing in pods as fast as if they are in the host namespace. And in order to get there, we had to pull off a couple of techniques. So one was to implement kubeproxy in BPF for the service load balancing, so we don't have to go through the net filter layer. And then we extended the kernel BPF side a longer time ago in order to have like a fast redirect in and out of the pods, so that we don't have to go through the upper stack and the host namespace. We can still utilize the routing subsystem out of eBPF. We can do route lookups there, so whatever your routing daemon is installing, like in terms of routes and so on, can still be utilized, but we don't have to go to the upper stack. And that helps. And eventually, we replaced the Weave devices. So we wrote specifically for Cilium's use case a new device driver into the Linux kernel, which is called netkit. And I will do a small deep dive later on. And yeah, the combination of that basically removed all the overhead. And this is upstream in Cilium today, in the Linux kernel, so you can actually try it out. So the core idea for this Weave device replacement was basically to enable better application scheduler behavior, because Weave devices, when the pod sends traffic that should be going out of the node, that's like inside the Weave driver, there's like a per CPU backlog queue where packets get enqueued, and if the system is under pressure, those packets, they will be picked up later on by the kernel soft ARQ daemon. And that causes latency issues because you have like two feedback loops essentially. So in getting rid of this internal queuing mechanism for traffic that's going in and out of the node, we can therefore also remove the NetNS overhead. So the other idea that we have was, okay, like Weave device is an L2 device, but we actually want to provide the choice for users. So you can have like an L3 device. That is the default case when you run Cilium together with netkit. Or you can also have like an L2 device if you want to use it as a direct replacement. L2 device is also useful in the context of KubeVirt, of course. But for the L3 device, then the pod network namespace doesn't have to care about neighbor entries. So it doesn't have to resolve them, because we resolve them into host anyway. And netkit still comes as a device pair, but in this case we have a primary device and we have a peer device. So this is roughly how it looks, and inside those devices we can attach BPF. And the core idea is the control plane, for example Cilium, will program all those BPF programs through the primary device. So an application in a pod cannot unload BPF from that device. So this is all managed for both devices from the host namespace, or like from that primary device. So yeah, this got merged into the kernel some time ago, and the improvement can essentially also be seen here. That's a flame graph where you can see where cycles are spent if you do performance analysis. And in the case of the Weave devices, you can see like those two towers where some of the work is done in the process context, and under pressure then the other part gets deferred. So you have like this double feedback loop. And basically in netkit, we move the BPF logic closer to the application. And when we do the route lookup out of BPF, we already know that, oh, okay, this packet has to leave the node. So I can directly push it forward to the physical device, and it can send it out. So all of this is basically still in the process context. So the application scheduler can account for those cycles in the application and therefore make better scheduling decisions. So doing a performance benchmark, what you can see here, like the very left side, the 63 gigabit per second is like the standard pod data path. So we had like two bare metal machines with 100 gigabit per second NICs and doing performance testing there. And the yellow one is if the iPerf or netperf, if they would be in the host namespace. And what you can see in the purple line, you basically get the same performance with those techniques that I just described with netkit. And the same for the latency. So we also get exactly the same latency numbers as if the application is residing in the host namespace. And shortly after we got the netkit driver merged into the kernel, actually some engineers from ByteDance reached out. And they were trying it out in a POC in their production environment. And they saw that with the help of netkit, they saw like a 12% increase of their connections per second that they were able to handle. And since then, they've actually migrated and rolled out netkit for their container workloads fleet-wide. And the same for Meta. So this was an interesting graph that was presented this year at the FOSDEM conference from a Meta engineer. And they compared Weave versus netkit for some of their production workloads. And they were looking at the P99 latency. And they were seeing with the applications they had that in case of the Weave device, when the system is under pressure, when there's high soft IRQ load, they saw like a P99 latency of 12 seconds. And when they switched to netkit, this was heavily reduced to 0.1 second, which is quite impressive. So yeah, they are also they are now using it as well, and they basically stated the same what we found as well earlier. So now the question is, can this also help in terms of VM networking? So this is again how the standard KubeVirt pod data path looks like. So we have the launcher pod. It's connected to the host with Weave devices. Packet go to the upper stack. There's a bridge. There's a tab where QEMU connects to. And yeah, in general, if you ask yourself, okay, like why even pod? Why even network namespace for that? Well, it's basically in order to control resources on the host, right? Like you still have your C groups, your namespaces, so that is still needed to contain the VM process in that sense. So when we move this over to netkit, this is essentially what it would look like. This is what you can use today with Cilium if you use latest Cilium version and reasonable modern kernel, then you can make use of that. And our first question was, well, how does the performance look here compared to the standard KubeVirt benchmark? So what we saw is a 13% better throughput in a TCP streaming bulk workload, and also the latency improved a little bit. So like 12% lower latency, yeah, which is already a nice improvement, but we still have like this bridge device, we still have the tab device, so like you can remove the network namespace overhead, but there's still overhead on the VM side, of course. So the question was, can we like fundamentally challenge this status quo with something else? The first thing that came to mind is, well, you could use SR-IOV. SR-IOV is probably the fastest you can get because it's hardware virtualization. Like you have a PF on the actual physical device that is in the host, and then you can spawn off virtual functions and move them directly into the VM. But there are issues with that because like the network traffic that is going in and out is now completely hidden from the host stack. So you don't really get the observability aspect. You cannot really do policy enforcement. For the Kubernetes service access, well, you can probably access load balancer services through hairpinning. You can probably access node port, but what about cluster IP? So really those capabilities depend on the underlying hardware. And you don't really get a unified container and VM experience. You can probably solve some aspects with DPUs, but then again, you're like hardware vendor dependent in terms of capabilities, what this can do, right? So another alternative that we then looked at was AFXDP. So not too long ago, QEMU got a new backend for AFXDP. And AFXDP itself is a technology in the Linux kernel that is providing zero-copy mechanism so that you can implement high-performance networking. It makes use of the XDP data path. So this is basically a layer where you can attach BPF inside the driver itself, so at the very earliest possible point in time where you can do something with the packet. And then you can push this into an AFXDP socket. So this is natively integrated into the kernel. You don't have to deal with out-of-tree drivers and so on, and you don't really have a vendor login because all the modern or reasonably modern NICs, they support AFXDP already. And yeah, initially it's actually quite interesting to, being in the kernel community for quite a while. Like I think like this dates more than 10 years back, where there was like the first initial proposal, which was actually targeted at accelerating VM workloads through a queue bifurcation. So you can like split the network card into different set of queues, and then one set of queues you would map all the way to user space, and you would expose that hardware into user space, and then you can use it for QEMU. But then the kernel community rejected that because of concerns that you're exposing the hardware directly to user space, and this is not something that the kernel typically does. Also in order to protect the user from from doing something bad. And then this whole thing led to development of AFXDP. So this is roughly how it looks. You have on the receive side, when packets go into the node, you have a BPF program at the so-called express data path layer, which is inside the network driver. And the BPF program can decide to push packets up to the local stack into applications. So this will go into the IP, TCP layers, and eventually into the application. But you can also redirect traffic into an AFXDP socket. And here you have a shared or like memory mapped region where the driver will then make use of that memory for the network packets. So they can be exposed into user space. And you have a couple of rings where there's coordination in terms of when the application can read traffic or send traffic. So yeah, this is roughly how it looks. But applying that to KubeVirt, there's a catch because the QEMU is basically launched out of its own network namespace. And typically for AFXDP, you need like a physical device to attach to bind to. And you don't have it in a network namespace. So the idea that we then followed was to extend netkit, like the virtual device driver there that we have in the kernel, with the idea that you have the physical NIC, and it has RxTXQ pairs, and you can actually create a new RSS context. So by default, you have, let's say, like traffic gets load balanced among, let's say, 16 RxTXQs, but you can reduce that to only load balance between 14 RxTXQs. So you have freed up 2 RxTXQs for something else. And then you can install rules to steer traffic to that 2 other queues, basically. And you can do that, for example, based on the MAC address, for example, based on the VM MAC address. And we then extended netkit to allow more than just like one virtual queue. So you can, for example, create a netkit device which then has 64 queues. And those queues, they can then be bound or like peered to a physical NIC queue. And then the idea with this whole process is you can move that netkit device into the Virt launcher pod, and then an application can bind against it. And then it can make use of functionality like AFXDP zero copy, but also IOU ring zero copy or defmem zero copy. So this is roughly how the picture looks like. So you can see here, like from the physical device, ETH0, we have 2 dedicated queues that we then expose into netkit, and then an application can utilize it. For the defmem, like the TCP defmem zero copy, if you're familiar with that, it's like it is technology to map GPU device memory for the network. So it's quite useful for AI workloads. The IOU ring TCP zero copy, it got merged actually this year into the Linux kernel, and that is quite useful for things like storage, like where you have like very bulky workloads. And then last but not least, AFXDP. So QEMU is one use case, but you also might have others. So just to do a small detour with AFXDP and IOU ring, because I think it's quite interesting. And for Cilium, we are basically, with this technology, with this extension for netkit, planning to support both of them. With AFXDP, you basically expose the full packet into user space. So you can have like DPTK-like applications. And here, like the upper kernel stack, like the IP TCP layer and so on, they are like completely bypassed. And this is useful for things like QEMU, as we've seen. With the IOU ring TCP zero copy, that requires newer NICs. For example, like the very high-end Broadcom one or NVIDIA ConnectX-7, which support header data split. And the idea here is like that the headers, they go into a linear section of the packet, and the data, they go into pages. And those pages, they are basically memory mapped with the IOU ring. And the packet still goes through the upper stack normally like any other packet. So it's not like a bypass, but it's basically to get that regular packet into the IOU ring application to do zero copy. And this is really useful for having TCP stream flows that go beyond 100 gigabit per second, right? Because like at some point when you get close to 100 gigabit per second, the biggest bottleneck becomes copying of data from kernel to user space. And here, this really allows to go beyond that, the zero copy mechanism. Anyway, so coming back to the netkit, queue binding, and how this can be applied to KubeVirt Pods. So the idea is now looking like this. So we have the physical device. This has a set of queues reserved for netkit. Netkit exposes them in the Virt launcher pod. And then QEMU is basically being started with the AFXDP backend this time. So you don't have a bridge device, you don't have a tap device, and you can make use of AFXDP. There's still a netkit pair down here. This is like for communication from host, like from applications in the host to the pod. And we did a prototype of all of this and some preliminary benchmarks, and I think they look quite promising. So basically in this case, Cilium is doing all the heavy lifting underneath what I just mentioned, what we need to do, like setting up the RSS context based on the VM MAC address, creating the netkit device, binding it to a physical queue from the physical device, and then there's a KubeVirt plugin that we wrote to launch QEMU with the AFXDP backend, which is then bound to netkit in the background. So with this, we got a 37% better throughput, and also the latencies were better across the board. So like roughly like 35% lower latency, what we've seen, which is quite nice. There's still a lot more work to do, to be done. One thing that we are working on is basically an XDP API rework in the kernel. Right now, XDP is still like one of the infrastructure points in the kernel where you can only attach like one program for a given device, and many other attachment hooks, they allow multiple programs. So that is like one thing we are planning to do, and also like to specify that you only want to have this XDP program run on specific queues. So you don't get into the overhead for traffic that is going into the host where you enter into the XDP program for no good reason. So this is something we are planning to extend. And once we have that, the next step that we are planning to work on is an AFXDP TX hook. Because right now, traffic that is going through XDP, we can do policy enforcement and observability there. But one thing that is still missing in the kernel is a TX hook where we can then drop or observe and whatnot traffic that is coming out of the VM. So this is the plan. And for the QEMU AFXDP backend, there are some low-hanging fruits, but also some bigger tasks. So like some low-hanging fruits, for example, is to use vectorized I/O to get traffic in and out of from AFXDP into the VM. So this is currently not being used, despite this benchmark that is actually a lot better in terms of performance, but there are still like some things where we can even further improve it. And then last but not least, I think like the really bigger item is to have like full zero copy into the VM itself. So that is, right now there's still a copy of the packet. Despite all that, performance is still better, which is quite nice to see. And yeah, now I want to show a small demo before opening up for questions. And in the small demo, you can basically see Cilium utilizing KubeVirt and this whole netkit queue binding, and where we launched the QEMU KVM as AFXDP. So I wasn't sure about the Wi-Fi here, so I did a small recording. What you can see here are two Equinix machines. They're actually the smallest ones, which is also nice because AFXDP also works with all the devices. And we are launching a VM there, and you can see, okay, those two machines, they can ping each other. Yeah. And next, what you can see here is we reduce the default context of the physical device to only utilize 14 RxTX queues. We create a new RSS context for our KubeVirt, and we install a flow steering rule based on the MAC address of the VM. And now we launch basically a KubeVirt VM with a given MAC address. So that is already a feature where you can specify the MAC address. It's already a feature that is upstream in Cilium, and we have a new annotation where we want to do this queue binding for the VM. And yeah, now the VM is being spawned. It's ready. And what you can see here is we enter into the VM and we can ping to the outside world. So all that stuff is now going through AFXDP, through netkit, and then the physical device. You can see it has connectivity. And if you look into the KubeVirt launcher pod, you can see here there's a netkit device. This is being used by QEMU for the connectivity. And if you look into the host namespace of where you have the physical device, you can basically dump the queue information of the physical device. So you can specify the if index and the queue index, and you can see that this is actually peered to the virtual device, which is in the other namespace. And yeah, last but not least, you can see that KubeVirt has been launching QEMU with the AFXDP backend, which was then bound against the NK, like against the netkit device. So yeah, that's the small demo to show that it works. And yeah, last but not least, I want to do a shout out to various folks who have been involved one way or another, either on netkit or on the AFXDP side or on the Linux kernel side. So yeah, huge thanks to all of them. So, and this is it. Like this, yeah, concludes the talk. And if you have any questions, please let me know. Thank you very much. Yeah.
Do you have to enable netkit for Cilium, or is that the default?
So the question is whether we have to enable netkit for Cilium or whether it's the default. So right now, you have to specify data path mode equals netkit in Cilium in order to utilize it. But we are planning in the future that once Cilium detects that the underlying kernel can actually has support for netkit, to automatically switch to it. But today, you have to opt into it. Yeah.
Is there any implication on the big TCP?
The question is there any implication on the big TCP? So I believe the Virtio NetDriver might support big TCP, but for the AFXDP side, that still needs to be supported. So this would be on the roadmap to also get working. But yeah, great question. Yeah.
I didn't see any of that stuff in your demo. It was just an annotation on the pod. So
Yeah.
you don't have to completely eliminating the attachment definition from the configuration.
So in terms of doing things like masquerading and so on, to have it routable, the plan is basically once we have that AFXDP TX hook, we can port over some of the Cilium functionality. I mean, like the code in general is quite reusable, so you already have it for XTP versus TC-BPF, but for the transmit side, then we can also use it there, and then we can also, if needed, masquerade. So yeah, that's still on the roadmap.
But if you go straight to the device, you no longer have to do any explicit definition of the netkit interface from the network attachment definition perspective. That's how you bring out expose like interfaces to the VM and whatnot.
Right.
And that's the workflow currently.
Yeah. I mean, so currently we have done this through this annotation, but yeah, that's, anyway, we can also catch up later, or like, yeah. Yeah. Does it work with jumbo frames? So for, like in terms of the XDP itself, some of the devices, they only support up to 1 page, but there's also multi-buffer XDP where you can have things like jumbo frame support. I think like from the AFXDP side, that should be possible to do. Like I've seen some NICs that do support it. Yeah.
Once you can do the kernel work, so you can do the multiple AFXDP applications.
Yeah.
Will multiple VMs on the same node mean you're consuming multiple queues from the physical NIC?
Correct, yeah. So, yeah. So that really depends on the amount of RxTX queue pairs that your NIC exposes. Some have very high amount, others might be more limited, but if that is the case, you can still always go to the current scheme where you can run Cilium today with netkit, but you still have the bridge and tap device, so that's like the fallback if you don't have this latest infrastructure for that. So that's still an option. Yeah. Does it support VLANs? That would have to be done basically through the BPF program, because like this is also the case today with XTP. If you want to handle VLANs, yeah, you need to handle it in the BPF code. So yeah, it can support VLANs. Depend. Say again? I mean, I would say it's like transparent to that. So it's like technology underneath that, and like that's one layer higher. So yeah. Yeah.
Would VMs with multiple interfaces work in this?
Well, the question is, would VMs with multiple interfaces work with this? Yes, so you can actually have multiple queue bindings and then expose multiple interfaces into VM through the same mechanism. So it would be possible, yeah.
So how would one specify, like in the manifest or the Cilium definition, like through annotations, like which interface to bind to which queue?
Yeah, yeah. All right. I'm actually out of time, but we can catch up after the talk as well. Okay, good. I'm also around at the Cilium booth or Isovalent booth if you have any other follow-up questions or comments, so happy to take them. Thank you very much.